they can be like this, for example. Although I want to go through some steps in the calculation because it's a fairly typical example asked in the exams. You have sum of the second derivative, which is the Laplacian plus a constant times u. The task is to approximate this differential equation on a given rectangular grid. Now my step sizes delta x and delta y don't have to be equal. N and m are integers. Question is, how do you approximate it? What's the local truncation error of your approximation? How do you solve the resulting system of difference equations? Let's start with approximations. I will do it quickly, but if you are doing it for the exam, you don't need to show the steps unless you are told. Otherwise, you need to show how you derive these relations. We know how to approximate the second derivative. In the x direction, for example, the x variable translates into n as a subscript. Second x derivative is approximated at everything is happening at x, n, y, m as the central point for my approximation. Second x derivative is approximated like that. That's our usual formula, divided by delta x squared. Second y derivative, we repeat this formula only with a different step size delta y, and the subscript in the y direction is m. The central point in both derivatives is u and m. We also need to add the constant a times u evaluated at the point where we're working, u and m. The total must be 0. This is our finite difference approximation. What's the local truncation error? If you go over the Taylor expansions, you prove, like we do for an ordinary differential equation, that the local truncation error is big O of what? The truncation error created by the approximation for the second x derivative, and we know that this is the second order approximation, therefore it's delta x squared, plus the truncation error from the second y derivative, delta y squared. And I can write it like that, saying that it's a term which is of order delta x squared if delta y equals 0, or it is of order delta y squared if delta y equals 0, or it is of the order of the bigger between the two, delta x and delta y. That's what matters for practical purposes. You want to know how accurate your approximation is in the sense of local truncation error. Then what I want to do is multiply through by delta x squared. I want to free up this combination. In front of the second y derivative, I will create delta x over delta y squared, which I will call beta. Then the a constant gets multiplied by delta x squared, and I will call it gamma. So this is an easy step. And I can rewrite my finite difference formula like that. Now, what you do next depends on how you are planning to solve this system of difference equations. And it's a huge system. As far as I remember, I did a video with filling in a matrix of the coefficients if you want to rewrite this entire system in vector form or in matrix form. Sometimes it is done if the matrix is not particularly large. And as you recognize a system of linear homogeneous equations, you can always rewrite this system as some matrix times u equals some vector of the right-hand side. You don't need to create a vector of the unknowns capital U, putting all these values u and m into a single column. And then once you've done that, then you just press the button a minus 1, the inverse, you get the answer. The problem with that is that first, it's very boring to write that matrix, although sometimes it's inevitable. But also from practical considerations, this matrix is huge. That's why you may not want to get involved with this method. An alternative is a relaxation method. Relaxation is synonymous with iterations. And one standard approach to a system of this kind that appears in elliptic equations is to arrange iterations by focusing on the u and m values that appear everywhere in here. So I will rewrite first of all, this system as u and m expressed in terms of everything else, and that will give me 2 plus 2 beta minus gamma. While I'm writing this, someone needs to check that the sign of the gamma is correct. Got the 2 already. 2 beta, that goes on the other side, so minus gamma. And the rest goes into the numerator. un plus 1m plus un minus 1m plus un m plus 1, un m minus 1, lots of subscripts. Right. And then the idea that belongs to Jacobi is to say that we shall create a sequence of iterations, taking the right-hand side from previous iteration left-hand side, which is just the u and m at new iteration.